In the last lecture, we solved one conventional question, and now in this presentation, we are going to solve one multiple choice question. I have taken this question from GATE 1999 exam, and in this question, we are required to find Fourier series representation of an impulse train denoted by ST, which is equal to summation n equal to minus infinity to infinity delta t minus n t naught. So the given signal is ST, and we are required to find its Fourier series representation, and we already know the complex exponential Fourier series is equal to summation n equal to minus infinity to infinity Cn e raised to power jn omega naught t. Omega naught is the angular frequency, which is fundamental type, and we already know fundamental angular frequency is equal to 2 pi divided by the fundamental time period. So in place of omega naught, we can write 2 pi divided by t naught. So St is equal to summation n equal to minus infinity to infinity Cn e raised to power jn 2 pi by t naught t. Now you will ask me what was the need to write omega naught in this form. You can see the four options and you will find omega naught is written in the form 2 pi by t naught. In option B and option C, you can see we don't have 2 pi by t naught, but we will not comment about the options until we calculate the coefficient Cn. This is the most important part of this lecture, calculation of complex exponential Fourier coefficient, and we already know the formula for Cn. Cn is equal to 1 divided by t naught integration over the range of fundamental time period. The given signal is St multiplied to e raised to power minus jn omega naught t dt. Now to solve further, it is important to find the range of integration, and for that we need to have the clear picture of the fundamental time period t naught. So we will quickly plot the waveform of the given signal. The given signal is St, and you can see it is the function of time. So the x-axis is for time. St is equal to summation n equal to minus infinity to infinity. N is integer and it is ranging from minus infinity to infinity. But to have the clear idea of fundamental time period t naught, it is sufficient to plot the waveform from n equal to minus 2 to n equal to plus 2. N equal to 0 is there in this range, so we will first plot the waveform when n is equal to 0. You can see St will be equal to delta t. So when t is equal to 0, we will get unit impulse. We are getting unit impulse when t is equal to 0 because delta t is the unit impulse signal present at the origin. Now we will put n equal to 1. We will have St equal to delta t minus t naught. When n is equal to 1, we will have St equal to delta t minus t naught. So this is the case of right shifting. We will have unit impulse. We will have unit impulse when t is equal to t naught. In the same way, when you put n equal to 2, you will have delta t minus 2t naught. So again we will have the right shifting, and this time the unit impulse will be at t equal to 2t naught. In the same way, we will have unit impulse when t is equal to integer multiple of t naught. Now when n is equal to minus 1, when n is equal to minus 1, we will have St equal to delta t plus t naught. This is the case of left shifting, and we will have unit impulse when t is equal to minus t naught. In the same way, when you put n equal to minus 2, we will have unit impulse when t is equal to minus 2 t naught. Similarly, the signal will go up to minus infinity. So this is the waveform of the given signal, and from here you can see we have minus t naught by 2 at this instant of time, and at this instant of time we have t naught by 2. So if we take this range for integration, we will have the total duration equal to the fundamental time period t0. So now we have the range of integration, and now we will perform the calculation 1 divided by t0 integration from minus t0 by 2 to t0 by 2. st is equal to delta t. In this range you can see st is equal to delta t. So we have delta t in place of st multiplied to e raised to power minus jn omega naught t dt. Now we will use one very important property of impulse signal. I explained this property in great detail while discussing the properties of impulse signal. According to this property, whenever you have signal xt multiplied to delta t minus t1, you will have xt1 multiplied to delta t minus t1. We saw the proof and explanation of this property, so we will not go into detail. Just remember to replace this t by t1 here. In this case, we can write Cn in this form. In place of delta t, I will write delta t minus 0. So Cn is equal to 1 divided by t0 integration from minus t0 by 2 to t0 by 2. Delta t we can write as delta t minus 0 multiplied to e raised to power minus jn omega naught t dt. Here e raised to power minus jn omega naught t is signal xt, and here in place of t we will write 0, because in place of t we have to write t1, and t1 is equal to 0. So after this we will have 0 in place of t. So Cn is equal to 1 divided by t0 integration minus t0 by 2 to t0 by 2 delta t multiplied to e raised to power 0 dt. E raised to power 0 is 1, so finally we are having Cn equal to 1 divided by t0 integration minus t0 by 2 to t0 by 2 integration of delta t, and we know integration of delta t from minus t0 by 2 to t0 by 2 is going to be 1, because area is equal to 1. So Cn is equal to 1 divided by t0 multiplied to 1, or we can say Cn is equal to 1 divided by t0. And as we have calculated Cn, our 99% task is over. We will simply put Cn equal to 1 by t0 here, and we will have the Fourier series expansion of the given signal st. It is equal to summation n equal to minus infinity to infinity 1 over t0, or we can write 1 over t0 here, which is the value of Cn. In place of e we will write exp representing exponential signal, and rearranging this we can write j 2 pi nt divided by t0. So you can clearly see option D is the correct Fourier series expansion of the given impulse train S. So I hope you now understand the complete process to find Cn and then finding out the Fourier series expansion. If you have any doubt, you may ask in the comment section. I will end this lecture here. See you in the next one.